Without further ado, Sylwia, warm welcome, and the floor is yours. The bandwidth is yours.
Okay, I will share my screen. First of all, I would like to say thank you, CPC, for the invitation and welcome. As you mentioned, I will be talking about Scythians and methods used for age at death assessment of examined individuals. Probably some of you, maybe most of you, don't know who the Scythians were. They were nomads who inhabited the Black Sea region in the early Iron Age. They were not only pastoralists, but also warriors, being among the first who have mastered the art of horse riding. They were mounted archers, known as one of the most battle-hardened of all the steppe people. They were fearless and unconquerable people who, after a series of war, occupy a vast area of Eurasia. Here is a map of Scythian territory, which stretched almost 7,000 kilometers across Eurasia, from the Danube River in the west to the Yenisei River in the east. Between 5 and 4 centuries BC, they played a dominant role in Eurasia. They created a Scythian kingdom with capital called Scythian Neapolis. They shown high social stratification. The culture is associated with enormous wealth of the rulers and gold and silver artifacts. From the literature, it is known that the main driving force of the expansion were cultural factors, including advanced technology and high social and military organization. Scythians form a unique nomadic group which, to gain such significant domination over other human population, had to differ from them, not only in terms of cultural factors, but also their biological structure and demographic feature. Despite the fact that archaeological research has been conducted for over 100 years, biology of this group remains understudied. Until 2010, mainly case studies and field reports were published. Only a few papers in key journals were issued. We are trying to fill in the gap in the knowledge about their biology. Our research are not only limited to paleodemography, we also conducting research on the health status, origin, morphological viability, diet, and physical activity. Additionally, we would like to extend our research to nomads from Central Asia, for example, Saka. Now we are trying to establish collaboration with researchers from that region. The histological material used in our study came from 3 archaeological sites in one village called Glinoe, which is located in southeastern part of Moldova. They are dated from 5 to 2nd centuries BC. Their chronology was determined based on grave goods. Additionally, for a few individuals, we performed C14. Those remains were recovered from about 150 barrows. The barrow was a mound of stones and earth raised over grave or graves. The Scythian chronology is divided into 3 periods: early, middle called classical, and late Scythian period. The excavation in the Glinoe brought skeletal remains coming from only classical and late Scythian periods. The Scythian barrows differ in terms of the size and the funerary offerings. Magnificent burial mounds were built for nobles with rich equipment. while commoners were buried in much smaller graves with scarce inventory or without any. During our research, we still come across challenges because of poor level of preservation of skeletal remains and the fact that age at death assessment requires multiple methods. We had to apply new research approaches. In only a few cases, estimation of sex was possible based on morphological traits. So this variable wasn't included in our research. However, in Scythian welfare were involved not only men but also women, with this evidence from what we know from the historical sources and archaeological data. So mortality pattern resulting in case of this group was rather not sex dependent. I mean, mortality resulting from military actions. At the beginning of the Scythian project, sample size was small. However, the number of individuals from the examined population has increased about 1/3 in the last 10 years. To my knowledge, it is the largest Scythian osteological collection in the world. We don't have permanent access to the skeletal remains, and they are located in another country, which limits to some extent our research. For example, like now, because of the coronavirus. The literature on Scythian is mainly published in Russian, so I had to learn this language. Age at death of particular individuals from the examined population was assessed using standard methods applied in physical anthropology. Age at death of subadults was assessed based on tooth development and eruption, bone fusion, and measurements of long bones, whereas age of adults on the basis of changes on the pubic symphysis, tooth wear, and cranial suture closure. For subadults, we can estimate age at death with higher precision than for adults. This is due to the rapid rate of growth and development processes, which make morphological changes in the skeletal system easier to notice in children than in adults. We had to apply multiple aging methods because each of them inform us about different lifespan stages. Tooth wear and pubic symphysis allow us to assess age at death only in case of early and middle adulthood, whereas tooth development and eruption and measurements of long bones are used for estimation of age of infants and children, bone fusion rather for adolescents. It should be highlighted that in skeletal biology, adulthood is thought of as beginning at age of 20. The first method, which was used for assessment of age at death of subadults, was dental development and eruption. Tooth development progresses from crown cast to apex. For each year of age, particular teeth differ in their developmental stages. What you can see in this chart, assessment of the development of crown and root of a tooth by reference to illustrated developmental stages allow us to determine age at death of subadults. The next method was bone fusion. The sequence of epiphyseal union is consistent and correlated with chronological age. By assessing the union of particular bones and comparing the observation with the chart of standard age at bone fusion, we can determine age at death of the individuals. For example, here, the head of the humerus is not fused to the diaphysis, so it means that this individual was not older than 23. the distal epiphysis is fused, so it means that he was older than 9 years. By assessing the union of different parts of the skeleton, we can quite precisely determine age and depth of the subadults. There is a strong linear relationship between diaphyseal length and age. We can estimate age and depth of subadults by taking measurements of diaphyseal length of long bones and comparing the results of the measurements to the reference standards. Then we unify age categories for subadults corresponding to each methods, as it is shown in this table. It was necessary because different methods had different number of stages, phases, which at the same time differ in age ranges. For the assessment age at death of an adult individuals, we used a thought method in which changes on the pubic symphysis are assessed. In young individuals, symphysial phase is characterized by a series of horizontal oriented ridges and furrows, and there is no defined edge between phase and ischial and pubic rami. With increasing age, the ridges disappear, phase becomes smooth and defined with a distinct rim. In last stages, phase become roughened and symphysial rim shows evidence of osteophytic lipping. In these methods, we assess age at death by selecting phase corresponding to the examined individuals. Dental crown aware over time. Here you can see the changes on the occlusal surface of teeth progressing with age. Here we have unworn teeth, slightly worn teeth, and heavy worn teeth of older individuals. By comparing the dental intuition of the examined individuals with the chart of age changes on the occlusal surface, we can estimate age at death. The obliteration of cranial suture occurs in strictly undefined periods of time, what makes it possible to estimate age at death of an adult individual. Here we have open suture, onset of obliteration, partial obliteration, and full obliteration. In these methods, we assess the status of closure of particular sections of cranial suture, and based on it, we can estimate age at the death of an adult individual. And in the end, we unify the age categories for adults corresponding to each method, similarly as it was done for sub-adults. Purely preserved and incomplete skeletons, we had to apply a different methodology. When only long bones were available for research, we checked if shafts and epiphyses were fused. The union indicated that it was an adult individual. Lack of fusion point towards a sub-adult. In such cases, only a rough division into two broad age categories of adults or sub-adults was possible. When teeth and long bones of sub-adults were not present, we took measurements of other bones, for example, cranial bones, and we used them for assessment of age at death, again by comparing the value to the reference standard. For each skeleton within the sample, age and death was assessed, and then the subjective probabilities was assigned, with which deceased belonging to the one of the following classes. Then such raw data were used for the estimation of age structures for Black Sea Scythians, the details of which will be presented by Jakub. Thank you.
So as you have heard from Sylwia's part, the assessment of age, it's an art as much as it, and there are so many uncertain elements that it just calls naturally for the use of statistical methods that do describe this uncertainty in some proper way. So that led paleodemographers and anthropologists to start considering Bayesian methods for these kind of uses. So what I'd like to start with is just to give you a brief overview of where Bayesian methods are being used in paleodemographic and similar anthropological applications. And a starting point is an overview paper, a very good overview paper by Lyle Königsberg and Susan Frankenberg from 2013, which also includes an introduction of Bayesian methods for anthropologists, where they identified several areas of possible applications of Bayesian methods, including, crucially for us, the mortality estimation under uncertainty in age assessment. There are a range of other aspects and other applications that are probably of less relevance for this talk, but I'll just mention them for the sake of completeness. So studies of disease and trauma, frequency of disease and trauma in the paleopathological or osteological studies of past skeletons. Likewise, the something that is important for forensic anthropology, which is an analysis and identification of human remains, including the ones that have been mixed together, for example, during moving of the remains from primary to secondary graves. And this is something that, in the context of victims of war, victims of natural disasters, is very important and can have important bearings for the subsequent court proceeding. Right? So this is a part of what could go in as an expert report to help the court establish the truth about what has happened in a particular case. And we have seen that, for example, in the former Yugoslavia, the anthropological methods were widely used, especially in relation to what was happening in Bosnia-Herzegovina. But going back to the Bayesian methods, what were the main arguments for using Bayesian methods in the context of paleodemography and reconstruction of age structures? So that there's a clear distinction, as those of you who are familiar with the philosophy of Bayesian methods know, there's a clear distinction between what's the probability of data given hypothesis versus what's the probability of a hypothesis given the data. So this is cited in the literature as the key thing that when you're doing things in a Bayesian way, you're asking the right questions about the age structure given the information that you have. And another very important aspect is that prior distributions, as long as they're informative and as long as they are appropriate, right, can supplement the incomplete or lacking information. I mean, what Sylwia mentioned is typical, right? So we have small sample of skeletons, and we need to make inferences of, we want to make inferences of that basis. So what we can do through priors, we can formally incorporate the so-called reference populations, so populations that help us map the measurements that we do onto age structures. And in that context, there have been suggestions that Bayesian methods are actually well suited for dealing with what's called in the literature the mimicry problem, where the estimates just mimic the age structures of the reference population. So there is an argument made by Jasper Bolsen and co-authors in a volume that on paleodemography from 2002, and this is a line of argument that was the paper that we'll be presenting in a moment, which has recently appeared in the American Journal of Physical Anthropology. I must say that we had probably one of the most thorough and best review processes ever. We had an excellent reviewer who really drew our attention into kind of interpretational details, such as the problem of mimicry. So, what are the limitations then? Of course, the role of priors in small data situations is going to be large. So the appropriate choice of the prior remains one of the key considerations. So the priors will be subjective. They will come from some other populations or from expert knowledge. So there would need to be some assessment of the quality. And small samples, if there is a disagreement between data and the prior, so if there's a data and prior conflict, then we may actually get back to the mimicry problem. So the prior can sort of again try to attempt to override the results and pull them in its own direction. So what is the possible, if partial solution is to carry out the analysis ideally for different measurement techniques in parallel, ideally to pretty standard thing in Bayesian analysis, do a comprehensive sensitivity analysis to different prior assumptions. So that needs to be borne in mind whenever we are thinking about applying Bayesian methods, paleodemography applications. But the method I would like to present is a hierarchical Bayesian model which was proposed by Caussinus and Daniel Courgeau in 2010. So what we are after, we are after estimating the structure, the population structure by age. So P is a vector of proportions summing to 1, and the data come in large C measurement classes or stages that sum up to the total size, right? So we have a vector P by age which we want to estimate, and we have a data about measurement classes adding up to the total sample. The model that Caussinus and Daniel Courgeau proposed is a Bayesian hierarchical model which has a multinomial likelihood with some structure parameter pi, and has a hierarchical prior structure. So it has we start with at the top level with a marginal distribution by age. So we have a prior across the age group, and have it from some tables about the tables with the kind of priors for pre-industrial populations which we could use. And then there are conditional distributions. So we are using priors from the reference population. Here is the reference population where this information is coming from. And what we need is conditional distribution by stage of measurement class given age. And the relationships are they're quite straightforward. What we can do in terms of statistical specifications, since both the age prior for P and the conditional priors for the observational class or stage given age are in fact describing proportions, right? So we can assume Dirichlet distributions for both. We can take, as I mentioned just a moment ago, right? We can take the prior structure by age from tables, and we can take the conditional priors from the reference population. Now to the example. So what we'd like to show now is the work that we did for exploring the use of different kinds of Bayesian methods for Black Sea Scythian population that Sylwia talked about at the beginning. So this is based on the paper that's just out in the American Journal of Physical Anthropology. And so what did we have at our disposal? The sample that altogether the 312 skeletons from 3 sites with a possibility of analyzing the skeletons by either social status, grouped into broad groups, you know, the nobles and commoners, with obvious sort of size differences between these two. So these are based on the artifacts that I was mentioned before. Also, we can stratify the analysis by periods, so early versus late variants. And of course, to make a life table analysis, we need to make some demographic assumptions. So to make it work, we either need to assume stationary population or a stable population. Otherwise, I mean, we have to assume something about the links of the skeletal sample with the sort of long-term population age structure. So in order to do that, we need either a stationary or a stable assumption to make it work. In addition, there are no problems with the lack of preservation of skeletal remains for children in many cases. And in fact, in our sample, in a moment, the numbers of children seem to be underestimated. You know, there are various reasons for that. Some cultural, some you know, physical, such as the acidity of the soil in which the remains are preserved. So the one thing that needs to be taken into account is the possibility of having to correct for the number of children, and there are also sort of demographic and anthropological methods that allow to do that by linking the size of the correction with you know, what may be a reasonable family size in that. And then we can relax the assumption of a stationary population to include possible population growth. So we can just assume a stochastic growth rate with some realistic parameters and some additional uncertainty on top, which is in fact what we did in this example. In terms of model specification, we have these three different life table models. And when it came to measurement, I mean, as Sylwia mentioned, it's quite a complex business. And in this sample, as you can see, that the picture was really complicated in that there were different sets of methods that were, you know, the team was able to use for different sets of the skeletal sample, and that broken down by children and adults. So what we ended up with is having altogether 31 measurement classes across all different methods. So how the model was operationalized? So we did use the Caussinus and Courgeau model that I mentioned a moment ago, with the reference population that was expert-based. So we sort of elicited from within the team, thinking what could be the expert-based equivalent of a 312 skeleton population if we assigned the skeletons to different age groups with different probabilities, as Sylwia was showing on her last slide. So what we did then was, of course, you know, we need to be mindful that we shouldn't be using the data about age structures twice. So we scaled the population so that each age group was of equal size, just to get rid of that problem. And then by using that reference population, we did test different specifications through quite a comprehensive sensitivity. In computational terms, the calculations were done in stan within R, and the estimations took between 5 and 20 minutes, depending on the model. So what was our subjective? How did our subjective reference population look like? I mean, here is just a graphical summary scaled from 0.1 for the white areas to 17, nearly 18 was the highest value, and you can see the mapping of age groups versus measurement classes or stages. So there is a clear patterning that you know, there is a sort of diagonal pattern in that table which we want to see, although with some uncertainty describing our lack of knowledge about the precise correspondence of the age and stage. And the final completing the specification, the age prior was taken from the textbook of handbook of Paleodemography by Sylwia which has a range of quite tables that can be used for this. So and you know, if for those of you who sort of are familiar with the properties of the Dirichlet distribution, so it's given the choices of the parameters, given how we scaled this reference population, you know, the estimation method will be working like that. It will be pushing the estimates away from the white areas and pulling them into the gray areas. So what we were hoping to see was that the age prior, when propagated through this reference population, will lead to some will propagate to the multinomial likelihood, and then what we would get is posterior estimates of age, but with some extra uncertainty related to age assessment. And this is indeed what happened. So the results, these are the results for life expectancy by age, by life table model, so stationary, stable with correction, or stationary with correction, and stable with correction. And you can clearly see that, you know, going back to Sylwia's point about the differences between adults being much less pronounced. So you can clearly see that on the example of the stationary population, that the uncertainty for adults is much larger than it is for children. Of course, once we add the correction for the number of children, we add yet another element which can bring in some errors into the picture. So that's how the intervals get widened in this example and in the stable population. But overall, I think the results we've got, the headline figure for the stationary population was 28 years for the life expectancy at birth. Once you correct for the number of children, dropping to about 18, 19 under different priors for the age structure. And we didn't find meaningful differences between social groups or within the burial period. So that was another indication that simply, you know, the skeletal material didn't allow to make firm conclusions on that basis. And when it gets really interesting, and here is another example where of an analysis that we were prompted to do by the reviewer, for which we are actually quite grateful, because it's sort of the analysis, the sensitivity to the choice of the reference population, and it will also go some way to answering Paul's question in the Q&A. So, as an alternative to our approach, what we did was we used a well-established reference population, but for one indicator. So that was the so-called Lisbon reference population from the 19th century, also tabulated in the handbook of Paleodemography. And also we used no reference population, so we just took a marginal information about the age. So what you can see is the results of the comparison. The blue and bluish shadings correspond to our results that I was talking about a moment ago. These are not life expectancy. These are life table deaths. So the axis. It's much clearer to see the differences on that indicator. So the red color talks about or depicts the estimates obtained under the Lisbon, so the 19th century reference population, where the nice thing about the Lisbon population is that there is an exact knowledge about the relationship between the measurements and ages. And the ages were well documented, and the measurements were also done quite carefully. So the tables are quite exact, but as you can see, there is a clear data prior conflict going on here, with the Lisbon population indicating the sort of modal deaths in the mid to late 30s, which we don't see in the Scythian sample. The Scythian sample, either with our subjective reference population or with no reference population at all, indicate a much earlier mortality peak, so in the 20s and 30s. And another thing that's worth commenting on here is that actually what was reassuring for us that our method with the proposed construction of a subjective elicited reference population prior worked as we intended it to work. So in comparison to the method or to the model which we did not use any reference population, what we got, right? So these are the dashed lines. What we've got instead is that the central tendency stays pretty much the same, and the differences are just due to numerical variation in the methods used, but the uncertainty increased. So what we got, or we think what we've got, is it's a more realistic assessment of the errors of estimation for the approach that is using the expert-based reference population. And another finding was the finding that was quite stable for all the specifications except for the Lisbon reference population, which we don't think is quite the right reference population to use in this case anyway, because of the data prior conflict. But one of the stable findings was that the zero probability of excess mortality amongst young adults, so think contemporary accident harm, did apply for Scythians. And this speaks back to what Sylwia mentioned at the beginning about the conflict and warfare and the lifestyle of nomads that involve quite a lot of fighting concentrated in age. So you can see that the zero probabilities of there being an excess mortality harm, depending on how you define an excess mortality harm, depending on which priors you use, but they're still all of them are still quite sizable. 0.6 at least, 0.8. So that was one of the results that was quite robust. So what can we say in summary? Right? In paleodemography and other areas of physical anthropology, the Bayesian methods are gaining in popularity, and the part of that is due to the ability of appropriate information a priori to substitute some of the data that may be missing or may be incomplete, or maybe just come from small samples with small sizes. And yet, just because these samples are small, for many applications, the errors of estimation do remain large, as we have demonstrated with the Scythian example. And what follows is the high sensitivity to the selection of an appropriate prior. And this is something where we thought that actually this was mostly an exploratory piece of work, but it can open up. I mean, some of the ideas here can open up quite interesting avenues for further work. So the first question that's of interest here is what to do in the case of the prior data conflict. Is it the case of the mimicry effect coming back and contaminating the results in the case the reference population is just not fit for purpose? Another question is what to do if you have several measurement methods, but for which you may have individual reference populations. There's a scope for using probabilistic mixtures of the results. And then the big question is if expert-based methods are used, how to construct appropriate prior distributions. And no matter what we do here, sensitivity analysis seems to be sine qua non. So there's quite a fair bit of reading if anyone is interested, starting from the edited volume by Hopper and Vopel and a handbook of paleodemography by Segui and Richer. Our first attempt in using the very basic version of this model in Journal of Anthropological Research, and some other overview papers like Bayesian statistics in archaeology, in case anyone is interested. So I would just say thank you very much. Thanks for everyone's attention. We'd like to give additional credit to Henri and Daniel with correspondence about some of the method, and of course the reviewers. co-authors Marta Klęskiewicz and Vitaly Sinica, and thanks to the